Hello everyone, this is Senior Design Team 7 from the Biomedical Engineering Department. My name is Adrian and my partner's name is Renz, and we are here to present our project, a brain-computer interface for restoring hand motion in patients who have had a stroke. But first we would like to talk a little bit about the background for this project. There are 15 million global cases of strokes recorded every year, with 795,000 of those being in the United States. One of the most common long-term effects of a stroke is the loss of mobility, which is what our project aims to help remedy. With this project, we aim to design an exoskeleton to restore motion to the hand with the opening and closing of the fingers. We will also develop a BCI which will control the movement of the exoskeleton with an EEG reader. The major project components include the EEG headset, specifically we use the Emotive Insight, the exoskeleton which spans from fingers to forearm, and then the interface between the two main components. In our case, we aim to use an Arduino Mega to transmit the information from the EEG headset to the exoskeleton. With the general outline covered, I will now move into my main part of this project, the exoskeleton hand. The exoskeleton can be broken down into several key components. The largest of these was the 3D printed pieces for the exoskeleton itself, which are designed using SolidWorks. The pictures you see on the right show a few of these pieces, the upper right picture being a SolidWorks drawing of an assembled finger, the lower right being a mount for the motor which was then fitted to the underside of the forearm, and the last image is a mount for the Arduino board, a second motor, and the battery. The last two main components are elastic and non-elastic cord, which were used to move the fingers. Due to the number of parts required to 3D print and the complexity of the other parts of this project, we wanted to keep the exoskeleton mechanism as simple as possible. In the end, we decided to attach elastic cord to the tops of the fingers, which was then also connected onto the top of the hand, with enough tension on the elastic such that when no other forces were acting on the fingers, they would remain in or return to a fully straightened position, as you can see in the top video. On the underside of the fingers, there was a non-elastic cord, which was connected to the motor and used to bend the fingers, as can be seen in the lower video.
And now we'll go over to the next part, which is the EEG and feature extraction. First off, the EEG chosen for this project is the Emotive Insight. It's a wireless EEG that has 7 channels, 5 of which are active and 2 are reference. It can record up to 128 samples per second per channel, and it has Bluetooth functionality. The following diagram describes the process of analyzing raw EEG data. First is the signal acquisition to get the raw EEG data. This requires Bluetooth connection between the Insight to a computer with Emotive software. Once the data is collected, the power spectral density is applied through a Python code, allowing for feature extraction, which will be discussed in the next slide. The resulting data will then be sent to the Arduino to command the motor to rotate a certain way. This process then repeats while the user is wearing the device. To test for feature extraction, 3 different states were utilized to discern 3 different hand movements: a resting state for a relaxed hand, a low workload state to open the hand, and a high workload state to close the hand. After the raw EEG data were recorded for each state, the PSD was applied to compare the ratios and sums of the alpha and beta frequency bands for each channel. Testing was done so that each state had 3 data samples. For the results of alpha and beta frequency band sums, channel T7 displayed the most consistent values. The resulting values shown here is used as thresholds to differentiate between the 3 states. These 2 graphs reflect the low workload and high workload results, of which T7 is highlighted for its consistency. For the resulting values for the alpha and beta frequency band ratios, channel A4 displayed the most consistent values. The resulting values shown here will also be used as thresholds to differentiate between the 3 states. These 2 graphs reflect the low workload and high workload results, of which A of 4 is the most consistent. Both channel AF4 and T7 will be used to differentiate between the three actions. These will provide thresholds for conditional statements used in the code. The provided table displays the ranges in which each action or state was recognized. These results will then be sent to the Arduino to perform a certain action. This video demonstrates the connection between the emotive insight which I'm wearing, the Python code which is executed by a computer, and the Arduino. Right here, the Python code is executed to collect the raw EEG data and run the PSD. If conditions are set to discover if the resulting data is a rest state, low workload state, or a high workload state. In this case, it's the rest state. This information is then sent to the Bluetooth of the Arduino, which is shown here. For our future plans, we would refine the exoskeleton parts to be smaller and fit more universally. Additionally, we would add a motor so that we could enable wrist motion along with the fingers opening and closing. We would also combine the two main parts of this project, the EEG and the exoskeleton, because due to the circumstances, the two parts became mostly individualized projects and were unable to combine for a finalized prototype.